Okay, welcome back, everybody. So last week we introduced witnesses. They're essentially gadgets which are encoded by the fibers of the witness cover, which is cooked up by just slicing some positive dimensional variety with the appropriate number of hyperplanes. But those hyperplanes are essentially arbitrary, so you can parameterize the space of linear sections of your variety, and you get some parameterized polynomial system. As long as that thing is square, you can do parameter continuation, and the story evolved from there, right? In general, we learned that this witness set, at least as described currently, is a triple. First and foremost, you have some equations which cut out the variety you care about as a reduced and irreducible component. You have a linear space of complementary dimension to your variety, which is generic. And you have numerical approximations of all the intersection points of your variety with that linear space. Now you can really think about the L and the S here. This is L and X. Generic complementary dimension. Okay. So this is first and foremost the data you think of as a witness set. You think about it as the linear space and the intersection points. But like, what is the F doing here? Why do I need the F at all? And the answer is because representing a variety just by a linear slice, and it's an awful way to represent a variety. Like if I just know these 2 points, that doesn't tell me that it's the circle. There are lots of varieties that go through those 2 points, right? So this doesn't seem like a very good one-to-one way to represent my varieties. And that's what the F's doing. So the F is giving us the ability to move the L around, okay? And what that means is those witness points, although if you fix the points first, an adversary could find a variety through them. If you reverse the turns you take with your adversary, and Alex is always my adversary in this course. So if Alex has another variety here, and I get to cook up witness points, I cook up random witness points, they will never be on Alex's variety with probability 1, okay? And this is actually going to be the idea basing our algorithms on several things we can do with witness sets. So in particular, we're going to go over the following things. So we can sample generic points. That's you can answer the point membership problem on it. These two together will give us variety containment. And variety containment is really just half of a variety equality algorithm. And then we'll do a short description of so-called regeneration techniques. It's like using witness sets to do something. Okay. Let me clean this up just a little bit. And introduce some of Oh, and I guess algorithm 0. There's a very popular adage in computational algebraic geometry these days, which is a variety walks in the door. What are the first two questions you ask it? And the first question you ask is, what is your dimension? And the second one you ask it is, what is your degree? Okay. Recall that that dimension is the largest chain of irreducible subvarieties, and degree is defined actually to be exactly the number of generic points in a linear space of complementary dimension intersected with your variety. Okay. So I wrote 0. You can compute the degree and the dimension of variety from a witness set because it's really trivial to do. The degree, so let's do this. Degree. So this should output the size of S. The size of S is the degree of your variety. The dimension of your variety given a witness set is just the codimension of L. L had to be picked generically of complementary dimension. So these are two affine invariants of your variety, which are really inherently baked in to the data type of a witness set. Okay. If you study algebraic geometry and you think about subvarieties in projective space, you really know that up to numerical equivalence, this is all the data of a variety, your dimension and your degree. But if you don't, forget what I just said. All right, facts. Intersection of two irreducible varieties is a proper subvariety of both. Contained in the other. It's just either. Corollary. Two distinct irreducible varieties of the same dimension intersect in a proper subvariety of. Well, we have two distinct irreducible varieties. The only way the intersection is not a proper subvariety is if the intersection is one of those irreducible varieties. Right. So if we intersect and we get X, for example, then we'll know that Y contains X. Which means X is a subvariety of Y. But the only m-dimensional subvariety of an m-dimensional variety is itself. So that would contradict them being distinct. The other that I want to state is a slicing lemma. I have an irreducible variety of dimension I. I have a linear space, which is generic of dimension. I want to conclude some stuff about the intersection of L and X. Yeah, that 1, 2, and 3. 1, 2. So I have something that is irreducible of dimension I slice it down with something generic of dimension m. Then the intersection is what you would expect the intersection is. That's what this says. In other words, every hyperplane which cuts out L will reduce the dimension by 1. Okay. Now, if the result of this, the result of this could be negative, by the way. So for example, if I have a curve in 3-dimensional space, then I is 1, n is 3, and I could choose m to be 1. I would be looking at, okay, so we have some curve like an iPhone headphones wire just floating in space, and I shoot a laser pointer just randomly in space. I'm not hitting that curve, right? And why is that? That's because 1 plus 1 minus 3 is negative. Negative dimension just means empty. That's how we're interpreting this here. Okay, so if the dimension of the two varieties that I'm intersecting, X and L, don't add up to at least the dimension of the ambient space, then I'm not going to get an intersection generically. Indeed, an adversary, Alex, could choose a laser pointer path, which would go through the headphones, but no, we're just randomly choosing it here. Almost all laser pointers won't touch your headphone cord. Okay, that's what that's saying. Okay, but if you are getting something non-negative, for example, I get something maybe that's 0-dimensional at the end of the day, so curve against a plane, a 2-plane in 3 space, that would give me something 0-dimensional. Then the degree of the, oh my gosh, X intersect L plus the degree of a linear space is 1. So the degree of the intersection is the same thing as the degree of the variety. And that's essentially by dimension, or sorry, by definition of degree. Because degree is the number of intersection points if you slice down by the appropriate number of hyperplanes. So if you have some variety has degree 30, and you slice with 1 random hyperplane, and then you have to slice with another to get finally many points, well, then the degree is 30. But if you slice it with just 1, the degree is still 30 because slicing with a generic second one is going to give you 30 points because the original thing had degree 30. So this is almost a trivial statement, thanks to generosity of the linear space. And finally, and this one's very nice, if X was irreducible, and we chose a random linear space so that the intersection has positive dimension, then the resulting intersection is irreducible. This is sometimes called Bertini's irreducibility here. Okay. Okay, great. Oh, no, I don't want to reset. No. So, algorithm 1. Sample generic point. Input. Witness set for X. Output. A point P on X. Which avoids any previously given subvariety of X with probability. Steps. 1. Use a random new linear space. Move a witness set to a new witness set. Return any element of SP. Okay. Okay. Alex is secretly thinking of a subvariety of this circle, which defines a notion of genericity. I have a witness set. I want to avoid Alex's secret locus. I don't know if these already do it, but as long as I just randomly pick another one, I apply homotopic continuation to move white line to red line with probability 0. Will either of these points be on Alex's locus? Okay. I think my impression of this algorithm when I first saw it was this is weak. This is not that special to be able to sample a generic. However, interestingly, this has pretty significant implications as far as algorithms in numerical algebraic geometry. And so the first one is point membership. And I'm going to put the closing theorem. What is a point membership algorithm? We'll write the algorithm first, what it should do, and then we'll cook up the steps. Input will be some point and a witness set. Again, X is an irreducible m-dimensional subvariety of C. Output. The truth value of whether or not P is an X. Okay. So here's the P. A witness set is the data implied by one of these linear intersections. How do you think we can check whether or not P is on our variety? Perfect. Pick a generic linear slice through P. Move your witness set to that linear slice. and see whether or not P is one of your witness points. P, I guess, and P. Now, of course, this is up to several numerical considerations of checking whether or not a given point is in a set of points when all of them are written as numerical approximations. So, yeah, there's a chance that I'm actually quite close to a point, and so when I move, it looks like I'm very close, but yeah, that's just what you get when you're dealing with numerical stuff. You wouldn't want an exact answer because then you wouldn't be able to put in numerical input to this algorithm. But if you really want to increase your confidence, so maybe your tolerance is like some epsilon for being considered equal, just choose a bunch of them, right? Yeah, that'll increase your confidence a little bit, but maybe not much.
So, F is a polynomial system.
Yes. The only role F is playing is allowing us to do these witness movements.
Why is this better than like trying to substitute it in F and seeing whether it is 0?
Yeah, that's a good question. The first thing is that F may cut out many components. Plugging it into F might not tell you whether or not you're on this component. It just tells you whether or not you're on one component if the residual is small. Right? And then of course, if an adversary comes and gives you some awful numerically, I mean, you can scale any polynomial system down by dividing by a billion, and now all your residuals look small. You know, yeah, but I would say that the main feature here is that it handles when F cuts out many components, so like the twisted cubic, right? Yeah, good questions. Because at the end of the day, I'm gonna want to be able to like compare irreducible components of different varieties.
Like also, twisted cubic has any component?
The twisted cubic, if you represent it as a square polynomial system, will have more than one component. As a consequence of the twisted cubic not being a so-called complete intersection.
Okay.
Yeah. So some varieties can't be represented as the zero set of a square polynomial system. Okay. And even if they could be, you don't want to do the symbolic calculation to find it. You'd like to be able to work with overdetermined systems. And they show up all the time, by the way, overdetermined systems. For example, let's say I'm looking at 5 by 10 matrices and I want the rank to be 2 or less. This is cut out by all the 3 by 3 and 4 by 4 and 5 by 5 minors of my matrix. That's a ton of equations for something that has still a significant dimension. So. Okay. So we have point membership, yay! And now we get variety containment, almost for free. I have two witness sets. I would like to know whether or not x1 is contained in x2. X1 is contained in x2. You have two varieties, one is not contained in the other one, the random point on one of them does not belong to the other one. That's how you even tell with your eyeballs when I draw two components, I would say. Right, so if I drew some other component here, how can you tell that these are different? Well, what you're actually doing in your head is you're going, oh, well, there's a random point on this curve and that doesn't belong to the other one. And so they're different. Right? It's kind of how you identify differences in subsets already. So sample a generic point and check if it's in the other line. Good. Essentially free. Finally, algorithm 4. The input is same as above. The output is x1 is x2. And it's one step. Just return algorithm 3 of the input and algorithm 4 of the input here, where and means the Boolean gate. We want algorithm 3. Sorry, this is still you're just doing two containments in opposite directions. Check if two sets are equal. You check that one is a subset of one, and then the other subset containment also holds. Right, so you just do two containments. You could probably think of an easier way to work on all of this to get variety equality using witness sets, but this will do. At least it'll convince you that such algorithms exist, which depend only on representing varieties in terms of witness sets and being able to move those around. Any questions? And these are the statements that allow algorithm 3 to work. Right? Because you're going to screw up if you sample something that's in the intersection. That's what's going to happen when you get something wrong. Right? This algorithm will fail if P was actually in the intersection of W1 and W2. But the intersection is a proper subvariety of both. As long as you don't have a particular containment. And so sample generic will avoid that predetermined subvariety. So maybe they're pretty intuitive, mapping out exactly which results are implying that these algorithms work. They're corollaries of these, but I think I'll move on unless there's questions. I'm going to say a short note about how witness sets can be used to solve the questions. My artistic abilities are feeling good. So I'm gonna try something in 3 dimensions. Here's an irreducible variety. It is the sphere in 3-dimensional space, as I call it, but of course it's the.
That's right. No, it's not.
Yeah. Of course not. Thank you. Great, great, so we got a sphere. And we want to intersect it with these 2 hypersurfaces here. Okay. All right, fine. Well, I can just do what I usually do. I do a total degree homotopy. It requires 7 times 3 times 2 paths to track. Some will go to infinity, throw those out. Some might have multiplicity, handle that, Cauchy endgame, blah, blah, blah. Okay, and that's one choice. Or you could do this this mythical polyhedral homotopy, which we haven't gotten into too much, and that'll just track mixed volume many paths. But a lot of times, even this BKK bound is an overshoot of the true number of solutions. Okay, and the following technique I'm going to mention is going to bypass these combinatorial bounds for degree counts and really go into geometric degree bounds. Okay. All right. This sphere has a degree 2, 2. And so if I intersect it with a random hyperplane, I get a curve of degree 2. Intersecting with random hyperplanes won't change my degree, it'll drop my dimension down 1 by 1. Okay. What if I intersected with a random degree 2 hypersurface? Now this is a result we haven't talked about, but if I take something X and I intersect it with some hypersurface of degree D, the degree of this is at most the degree of X times D. It's a souped up version of Brysiewicz. So if you think about one equations and you do Brysiewicz theorem, well, the first one is something of degree D1, the next one is something of degree D2, and you'd get this product as your bound. Okay. Okay. So let's say we started with a witness set. So I have my F, and I have 2 equations for hyperplanes, so 2 linear forms. Okay. Now I'm regretting my artistic arrogance here. Okay. So this is a line, but again, you can really think about it as 2 hyperplanes. Intersect. All right. I'm going to move this by just changing one of the hyperplanes, an H1 prime. So let's say this one's H1, and this one back here is H2. I'm just getting some other line here, right? And I can track the points. S1, S2, S1 prime, S2. Okay. Right? So far, so good. Now here's some fun. What are the solutions to this system? Remember, on your first homework, because this whole class is really baked into the first homework. You studied how to write down equations for unions of varieties, right? So this is the union of FH1H2, i.e. S1 and S2, and FH1 prime H2, which is S1 prime and S2. So you know the solutions to this. Right? So here you have S1, S2, here you have S1 prime, S2 prime. Here you have S1, S2, S1 prime, S2 prime.
What is the product of X1 and X2?
What's your question?
Like, what does it written adjacently, like, is it union, is it product? Like, is it a equation?
This here?
Yeah.
These are equations. This is a product.
Oh, okay, those are equations.
Equations? Yeah, I probably should have used like a lowercase l instead of these h's, because I like h's for the geometric hyperplane. But these are equations. Okay. So how do you make the middle thing zero? Well, you either make one of the factors zero or the other one. Okay. Old news. But now you have something that looks like geometrically x, something of degree 2, and something of degree 1. And so you can do a homotopy here to say, oh boy, I don't have anything of degree 2. Okay, I want to solve for this. We're going to use the third one, H1 prime prime, S1 prime prime, S2 prime prime. Okay. Great. So now I just moved witness sets twice. And I found the solution set to a polynomial system, which kind of looks closer to the one I want to solve. And I can do a straight line homotopy like this. So I'm just traveling in the space of degree 3 polynomials. Yeah, my start system is one that's easily solvable, because it's the product of a bunch of essentially linear systems here. So these are found, and their solutions are found via witness set moving. And then you kind of take this union of these three witness sets and you deform this union of three lines into something that is irreducible, an irreducible cubic hyperspace. And then when you get the solutions to this, what do you have? You have a witness set for this variety. Okay. So let me write this down a little bit more generally and algorithmically. And I'll give you an important subtle feature. Here. What do you got? You got a witness set for some variety. And you want a witness set for that variety sliced with some hypersurface of degree t, defined by G. And this should maybe be L1, Ln minus N, Lm. L2. What do? Cook up D copies of the witness set, just by moving it around randomly. That'll give you the solution set. Sorry, this is HIL2. You're moving just one of the hyperplanes around randomly. This will give you the solution set to this start system, F, the product of the HIs, and the remaining L2 to Ln. Okay, and now you move that G prime to be G in a straight line homotopy. What you will end up with is the variety defined by F and G, and a bunch of generic linear forms. So that's a witness set for the variety cut out by F and G. And this whole process is called regeneration. And there are some issues. Okay, so as written, this is incorrect. Why? Because I really don't know the geometry of F intersect G. Right? Like, bad things can happen if G is just a repetition of something in F, for example. Right? We'll still get endpoints to our homotopy paths, but they'll lie in positive dimensional components. Right? Or they'll have some multiplicity structure, which we haven't discussed how to handle. Okay. But the idea is there. So I guess you're returning now F and G as your equations. That results of homotopy continuation there. That's your triple. Okay. And now I'm going to correct the output of this algorithm so that what's being said is true. What are you really getting? You're getting the equations, you're getting the linear forms, or the linear space, I guess, of V of this. Making this distinction. And you're getting a collection of numerical approximations. These are the endpoints of the homotopy. And those endpoints will contain a set S for which this is really a witness set for that variety. Okay. Such triple is called a witness superset. Okay. So this is a way to get a witness superset for the intersection of a variety in a hypersurface given a witness set for that variety. Honestly, I don't use this technique a lot, but if I were in a situation where I found that that I'm trying to solve a polynomial system and the BKK bound is significantly smaller than the Bezout, then I might choose to do this. 21. Okay, great. And there's a nice picture in the notes, which I'll upload a little bit. I'll give you a teaser for next class. And I think next class is where you will really see the power of witness sets. So far, I've hopefully convinced you that it's one way to represent a variety. It's nice, you can do all these algorithms, but I don't know, maybe you're not convinced yet. Okay. Okay, so you have some variety upstairs. And you have some projection of this variety. So for example, I don't want you to think branch cover, I want you to think something like this. Okay, like a space curve projecting down to a plane curve. And you have equations upstairs. And this is a variety. I guess you want to take closure just to be careful. This is some variety, but you don't usually have equations for it. And the process of getting these equations from the equations upstairs is hard. It's the topic of so-called elimination theory. And this is a symbolic suite of algorithms that you'd be learning like the computer algebra side of computational algebraic geometry. And it takes a long time, it's really hard. However, and I'll just leave you to think about how to do it. If you have a witness set for the thing upstairs, getting a witness set for the thing downstairs is almost trivial. And that is because a witness set is a geometric representation of a variety, and projection is a geometric operation on varieties. So they play nicely with each other. Whereas projection being a geometric operation on varieties, it actually does funky stuff to the algebra side. Okay. And so that is today's lecture. Thank you very much.